Hello friends, in last video we discussed about convergence and measure of a sequence of functions. So in continuation of that, today we will discuss Riesz theorem. In last topic we had discussed that how uniform convergence of sequence of functions implies convergence in measure also. So in continuation to that, as a converse of it, we can say not exactly converse, but in a relation to that, the Riesz theorem says that if we have convergence in measure, then it implies pointwise convergence almost everywhere. So let us watch the video. So Riesz theorem says that if we have a sequence of functions which is converging in measure, then there should exist a subsequence of that sequence which converges to the same function which is limit of that pointwise almost everywhere. So here we are concluding what, that convergence in measure gives pointwise almost everywhere convergence to the same limit. Okay, so let us do its proof. So what the proof says, so for that we will assume that this f is a sequence of functions which is converging to a function f in measure. So after considering that, what we have to do, we have to write the meaning of it, and the trick is that what we will consider the convergence in measure definition. For that, the eta we will take as 2 to the power minus r for any natural number r. So for every natural number r, the eta will be taken as 2 to the power minus r. And over that, what definition we had written in that remark, which was an equivalent condition for that definition. So we consider that limit part, which is limit of the measure equal to 0. So for that we write that measure of this set means for each epsilon it should be less than epsilon after some naught. So we use this part for writing the definition of the convergence in measure. So with this one, we will consider the another trick is what, for that this epsilon, that also we will take as same 2 to the power minus n. So we are going to consider this one, and this is going to give us this expression for our definition of convergence in measure. The expression becomes the measure of this set where eta is this part is less than this epsilon. So we can abbreviate this as that for each epsilon, for each r as a natural number, the epsilon taken as this one, what we get, the measure of the ER set is less than 2 to the power minus r for all n greater than or equal to nr. Why we are taking not n naught, we are taking nr, because for each when we write n naught, it depends on epsilon. So here our epsilon is what? Here our epsilon is going to be 2 to the power minus r. So depending on epsilon, that for every r it is n naught. So it cannot be common n naught. What we are going to write it? We are going to write it as epsilon as nr. So for each r means we get nr. So nr can be any natural number starting from r equal to 1, it can be 1, 2, 3 or something. Then for r equal to 2, it can be anything else further. Like this it will go on, and therefore what we are going to get here is this measure of the set is less than this thing for all n greater than or equal to nr, where er set is given by this thing. So this covers the definition of convergence in measure in these two conditions 1 and 2. Now what we have to show, we have to show that there exists a subsequence of the given sequence which converges pointwise almost everywhere. So let us see that the points where this convergence is not there, means pointwise. So the measure of that set should be 0. So we will create a sequence this way, and we will prove it's the set of points which is violating this pointwise convergence has measure 0. Okay, so as we observe from the definition of this set itself, it tells that f and x and fx differences becoming more than something epsilon or something. That means the convergence is not there, so it seems like violation set. So what the trick we are going to do here is that for any natural number k, we will write set ak. What we will do, we will write a set ak. For any natural number k, we will write a set ak, which is going to be what? That all these ERs are starting from k to infinity. For example, k is 1, then E1, E2, E3, all unions up to infinity. If k is equal to 5, then E5, E6, E7 and so on. So let us collect all these sets and take their union. So these are all the points we will collect which are not in the set. Why not in the set? Because in these sets the convergence is not there. So let us come out of these sets. So with that, what we are going to have? We are going to have that in outside those we must have this thing, because convergence of measure is there. So we will take that after means this one we get, means for these things we get this one as mod of f and k r. F and r is thing is less than outside these points. So in particular for n equal to nr, in particular what we get this condition, which is this one. And now let us see what is this going to give us. This is going to give us this condition, and where this epsilon equal to eta equal to this is 2 by 2 to the power r. Okay. Now as r tends to infinity, so this subsequence f and r of functions at this particular x will converge to by this definition, because as r tends to infinity, this will tend to 0. Therefore by sandwich theorem what we get, that this sequence of numbers converges to fx. So what we observed? We observed here that if we take all the points which are not in their unions, that means which are not in AK, so we get the convergence there. So what we will do? We will collect all these points for each k, because we had fixed somewhere k. So for that particular k it is happening. So let us consider all the k. Let us take all common points where the convergence is there. So we can say this is intersection of k from 1 to infinity, and that becomes the set A. And over that we are saying that the convergence is there out of A points, because we are considering all the points which are not there. So out of the set A we are considering that. So over that set A the convergence is there. So we have got a subsequence where the convergence is outside where, which is the convergence there. So now if the convergence is pointwise convergence of this subsequence is in E minus A. So on A, if we successfully prove that the measure becomes 0, we are able to prove the property of convergence almost everywhere on set E. So that is what we are going to do now. We will prove measure of the set equal to 0. So let us consider what is A. A set is intersection of AKs. So it is intersection of AKs. So if we write it as intersection of AKs, then definitely it is contained in each AK. Because it is contained in each of AK, so we are writing this AK here. So the measure of that set, why? The intersection is subset of it. So we consider the measure of A, it becomes less than equal to measure of each AK, because A is intersection of all AK and then becomes subset of it. Therefore, further what we will measure of union. So let us apply countable subadditivity property that says that it is less than equal to measure of each individual and then taking sum up of that. So countable subadditivity of the measure. Then this gives me what? That measure of each ER. Now if you see that what is ER, we have condition number 1 which says that measure of ER is less than 2 to the power minus R. That is convergence by measure definition. We had already got this condition. So that gives us that this full sum is strictly less than this summation. And now let us see what this summation is all about. This infinite series, which is geometric progression, it will have sum defined like this, and what sum we will get? We will get the sum as 1 by 2 to the power k minus 1. So what we have got? We have got measure of A is less than equal to 1 by 2 to the power k minus 1 for all k. So if we take limit of k tending to infinity on both sides, so what we will get? That measure of A is less than equal to 0. We will get like this one. And always we know that measure is non-negative, therefore the measure has to become equal to 0. So we achieved this what? That the sequence converges to this function f. There is a subsequence which is converging pointwise outside A, and A has measure 0, so the convergence is almost everywhere. So that proves the theorem that the convergence in measure of for the sequence of functions, we have a subsequence which converges to the same function. How? Pointwise almost everywhere. So that proves the Riesz theorem. And what is the conclusion of the Riesz theorem? Let us compare it with the result which we did in previous video. That was saying that uniform convergence implies convergence in measure. So if it is saying convergence in uniform convergence implies convergence in measure, so this Riesz theorem is saying what? It is saying something as not exact converse of this one, but it is saying if we have converse in measure, we can have not even pointwise convergence full, but a subsequence. So it is a little weaker result, the sort of converse, but not exact converse. So that is all about Riesz theorem. So that's all about the Riesz theorem in the topic convergence and measure. So we will meet next time again in the next video of some new topic. Till then, take care. Bye bye.